Good afternoon, everyone. My name is Jacco Thijssen. I'm a professor of mathematical finance in the Department of Mathematics and the Management School at the University of York. With me on the flight deck today is Dr. Nick Huberts, who is also at the University of York Management School and who is the co-author of this work. So he is there to answer all the questions and to make sure I don't say any really silly things. Just before I start, a couple of housekeeping things that I've been asked to share. So here's just a slide. Main item here, I think, is a request to use the Q&A function rather than the chat function, because in the Q&A function, you can upvote particular questions so that they rank higher if more people vote for these questions. I'm happy to take questions during the seminar. If they're put in the Q&A, Nick will alert me to any pertinent questions that that might need immediate answering. I'll make sure that there is time at the end for a longer Q&A session, and a link of the to the video of the webinar will be sent to you later this week. Okay, let me just get started then. Okay, so this is some work that we've been doing recently. Well, we started this in May, I think, around the question of optimal timing of non-pharmaceutical interventions during an epidemic. It should be obvious what the motivation of this work was, but we wanted to focus mainly on the timing issue. So the main idea being that you need to decide not just to have non-pharmaceutical interventions in an epidemic like a lockdown, but also when to start it. And once you've started it, when you should exit those kind of measures. And of course, in May, when we started this work, this discussion was only just starting. It was pretty obvious that a lockdown had to be instigated, but well, I mean, there was a vote in Parliament only yesterday around exactly these kind of issues. When should you lift those kind of measures? And so the debate is very much about the balance between the public health and health system consequences of not imposing a lockdown. So the fact, if an epidemic runs rampant through a population, it might overwhelm the care sector. It might impose unacceptable health costs on society in terms of the number of people infected. But of course, that has to be balanced against the economic and other health consequences of having a lockdown, and that would include, for example, mental health consequences of stopping to a certain extent daily life. So that's the motivation of this paper. It's trying to look at this balance between these two effects. And I'll give it away straight. The takeaway message of our work is that you should go in early, you should go in hard, but don't bother if you're too late. So if you find out about an epidemic too late in the cycle, I'll explain later what I mean by too late, then it's better not to impose a lockdown at all. To coin a phrase, no lockdown is better than a late lockdown. So what we do in this paper is, so we're trying to build a very simple model. We start with a very simple epidemiological model, so-called SIR model. I'll explain later what that means, of an epidemic on which we then bolt onto a decision maker's problem. You can think of the decision maker here as a social planner. So we're looking at this problem from the point of view of a social planner who has to decide when to enter a lockdown, which would reduce the infection rate, and then subsequently when to lift a lockdown and revert to the original infection rate. So the whole idea here is that we have a simple model wherein a social planner has an option to reduce the infection rate, of course, at a certain cost, and then to lift that measure and go back to a higher infection rate, but a lower cost. We assume throughout this paper that these options can only be exercised once, right? So we motivate that by saying, okay, it's politically difficult once you've lifted a lockdown to go back in, as we have actually seen in recent months. But in any case, we think of this as a first step towards analyzing these issues, and of course future work would expand on this. Again, I get to talk about that more later. So we assume that this social planner has an objective to minimize the present value, so that today's value of all future costs of the epidemic and the lockdown. So these costs are discounted at a particular rate, and the expected stream of these costs, the expected present value of the stream of these costs, should be minimized. So that's how the actions are going to be taken. So mathematically, what we do is we solve two nested optimal stopping problems, as they are called, in a continuous time Markov chain. So throughout this talk, the outline of this talk will be that I'll talk you through the setup of our model first. So I'll talk about the epidemiology underlying it, after which I'll say something about the cost structure, so the decision-making structure of the model. I introduce you to the actual formulation of the problem. I'll say a little bit about the solution of the model, how we solve these problems, and then I'll talk about the consequences, so the policy implications, if you like, of what we find. As I said before, do feel free to put questions in the Q&A. If there are particular issues that I need to clarify, then Nick will alert me to that, and I'm happy to take those kind of questions throughout. So in terms of the epidemic modeling, we start with a population of size capital N, whatever that may be. Finite, of course, and on that population we're going to define a state space on which we define our continuous time Markov chain. And the state space here consists of the number, at each point in time, the number of infected members of the population and the number of recovered. As I said before, we use an SIR type model. So SIR stands for susceptible, infected, recovered. So that's a very basic model for an epidemic. So it's the kind of disease that appears and then at some stage disappears. I'll talk later a little bit about what would happen in a model for an endemic disease. That's something we can't deal with here. So in this kind of framework, there are three states. An individual member of the population can be susceptible, can be infected, or can be recovered. Again, we do not allow here, and once recovered, they'll never get the disease again. So we assume that once a patient has recovered from the disease, they're immune forever, or at least within the time span of our model. Again, this can be extended, and I'll say something more about that later on. So now, obviously, so we've got three states, but our state space is only two-dimensional, because if you know how many infected people there are and how many recovered, then you also know how many susceptible people there are. It's just the population size minus the number of infected minus the number of recovered. So that's our state space. And on that state space, we're going to build two Markov chains. depending on what we call the mode, the policy mode that we're in. And you can think of mode 0 as, you know, leaving the epidemic go through the population, this sort of herd immunity, if you like. And mode 1 is going to be the one where controls are in place. And when I talk about controls, you can, you know, just, it's probably easier just to think of lockdown. I probably will be using lockdown and controls as synonymous anyway. Now, for each of these modes, we then define an infection rate and a recovery rate. So in our model, we have a continuous time model, and infections and recoveries take place according to Poisson arrivals. So the inter-arrival times between events are exponentially distributed, and in each small interval of time, either nothing happens, or a susceptible member of the population becomes infected, or an infected member recovers. And the rates at which these recoveries and infections and recoveries respectively arise are given by these equations here. Again, these are very standard specifications from the literature. And we basically assume that both arrivals, so new infections, and recoveries are proportional to the number of infected in the population. So the more people are infected, the more likely it is that someone is going to recover, and the more likely it is that someone is going to, susceptible member of the population is going to be infected. So it's proportional, but proportional depending on a particular parameter. So there's a parameter beta, which we assume is mode specific, which gives you sort of the likelihood of infection. And we assume that the infection rate, the probability of infection in mode, you know, under herd immunity, is higher than the probability of infection when you're in lockdown. And then we have a recovery rate, which we assume is equal in both modes. It's not crucial that these are equal. You can easily make them unequal, but in our minds, what a lockdown does is, if lowering the infection rate, it doesn't actually make recovery any faster. Okay, so we assume those recovery rates to be the same in both herd immunity and in lockdown. So together, these two parameters, this beta and this gamma, lead to a reproduction number. So that's usually what people in the literature on epidemiology look at, and that's just the ratio of those two. Okay, and again, that's going to be different, of course, for the different modes. That's going to be mode dependent. Let me skip this slide. So basically, we built on this a probabilistic structure. Given these infection and recovery rates, we construct the appropriate probabilistic structure to make all this work. But let me just show you, to give you some feeling for what this chain looks like. So here we have a situation with, say, 4 people in the population. And so I've got all the states up here and down there. And the dots here, the dots basically give the states that you have a positive transition probability for. So if you're in the state where one member of the population is infected and no member of the population is recovered, then there are 3 things that can happen in the next small interval of time. Either you stay where you are, or the infected person becomes recovered, or you get another infected person. The open circles here denote absorbing states. So once you've reached an absorbing state, for example, this one here, 0, 4, if no one is infected, but 4 people are recovered, then of course there are no susceptible people left anymore. There are no infected people anymore, and that means that the chain ends. So I just saw a quick question in the chat. The I value, so because we are in continuous time, everything here, the law of motion is defined essentially. Essentially what's going to happen is you're going to get a differential equation. So you can think of this as the state at time it, and this state is then at it plus a small period of time, okay? And then the transition probabilities are given. So all these rates are instantaneous, yeah? So you have to be a little bit careful. If you're thinking of a discrete time model, then you're absolutely right. You would put an IT on this. Of course, yes, you can think of it in that way if that makes it easier for you. These infection rates are the number of infected people that I showed you before here. Whoops. Yeah, you can think of this as the infection rate at time t if you have IT if infected and RT non-infected. And that gives you then the rate over a small short interval of time. Another way to look at this is as a lattice. This basically gives you the same information as the slide before, but it shows you some the paths that the chain can take. So I think again it's important to realize that this is not, because it's not a discrete time model, we're not talking about a state at time 0, a state at time 1, a state at time 2. These time 1, time 2, time 3 are all randomly selected. Yeah, they're not of equal length. There is at some point in time a transition, and that transition can go from, for example, the current state 1, 0 to 0, 1 or 2, 0. And in the meantime, the state remains 1, 0. Okay? Right. So that's sort of the model of the epidemic. Very standard. You can find it in any textbook on this kind of subject. So what about the cost? Again, we try to keep things as simple as possible. So we're assuming that the costs, of course, are state dependent. So at any point in time, if the number of infected members of the population is I and the number of recovered is R, then we assume that the total costs at that point in time are going to be given by a fixed cost per infected member of the population, plus, if you are in the lockdown mode, a sort of running cost of the lockdown. Okay, so this is an estimate of how much the lockdown costs, say, per day. We're taking a linear structure with constant costs of lockdown, constant costs per patient. Again, that's not crucial in terms of the results that we have. It just makes everything a little bit simpler. But you could make this a convex function if you wanted to. For example, you could make it. Yeah, you could play around with this. Okay, and we have some robustness analysis actually later on where I show you where we do make where we do tweak these costs, and it doesn't really change the qualitative picture very much. So that's the idea. Every infected person imposes a cost on society, and every day spent in lockdown poses an additional cost. And of course, the whole idea is that by introducing a lockdown, you're increasing this cost, but you're hoping to decrease that cost. Okay, I've said that. In addition, we assume that there are some switching costs. I mean, switching on a lockdown isn't straightforward. All of a sudden people have to start working from home. You have to buy cameras, you have to buy Zoom licenses, a desk chair, all that sort of stuff. And we assume that these switching costs are sunk and that we have switching costs that are positive for entering lockdown. And I should have said non-negative for lifting lockdown. Actually, in our numerical examples, we assume that this cost, if memory serves me well, is 0. So K01 just simply says if you change the mode from mode 0 to mode 1, so from herd immunity to lockdown, then you incur this particular cost, and in the other direction you incur this cost. And these costs are sunk. So once people have bought all these cameras and stuff, if the next day the social planner were to announce that lockdown is over, then sorry, yeah, you're not recouping those costs. We assume that there is a discount rate, a social discount rate for time, which we parameterize here by rho. Again, this is very common in this kind of literature to assume a social discount rate. The government actually has guidelines on these kind of things. If you look at the Department for Transport's guidelines as to how to value infrastructure projects, for example, you'll see that there is a discount rate of, I believe it's about 3.5% per year. Okay, so what is now the planner's problem given what we have in mind? So I'm just going to build this up bit by bit. So if you never impose a lockdown, then from time 0 to infinity, so we're assuming here an infinite time horizon to make our lives a bit easier. From time 0 to infinity, at each point in time, you incur the cost of having I infected and R recovered at that particular point in time. You're in mode 0 because there's no lockdown, so you're in the sort of herd immunity state of the world, discounted at the rate rho. And then, of course, you take the expectation because of the randomness here. Okay, so we're assuming to a certain extent that the social planner is risk neutral, or if you want, you could say that the social discount rate rho includes a risk compensation, market price of risk, if you like. Yeah, so that would just simply be the cost of starting at time 0 with I infected and R recovered. For I and R arbitrary, of course. Yeah, so at every point in the state space, this would give you your expected costs. So just to introduce this notation here, this is the expectation in mode 0 if you start at time 0 with I infected and R recovered. So now suppose that you decide to enter lockdown at some time tau 1, but that you never lift it. Then this cost before lockdown is no longer incurred from time 0 to infinity, but only to time tau 1. And from tau 1 onwards to tau infinity, you're getting the cost of being in lockdown. So it's the cost function in mode 1. Of course, switching from mode 0 to mode 1 means you incur the sunk costs. So those have to be added. But of course, they are incurred at time tau 1, so they have to be discounted to time 0. Okay, so that's once you decide to enter at time lockdown in tau 1 and never lift it. Now suppose that the lockdown is lifted at some time tau 2, which is later than time tau 1, of course. Then what happens? Well, the lockdown costs are no longer incurred from tau 1 to infinity, but only between times tau 1 and tau 2. And after time tau 2, you are back at the cost function that you had before. So the before lockdown cost function. Until time infinity, because we're assuming that you can exercise these options only once. So once you're here, this is it. Of course, when you move from the lockdown mode to back to herd immunity, if you like, you incur some costs, the K10 costs, which may be 0, and they are discounted back to time 0 as well. So this gives you the, if you have a plan, if you say, I'm going to introduce lockdown at time tau 1, I'm going to lift it at time tau 2, then this is the value, if you like, of that policy. Of course, the whole point now is that you need to decide when it's optimal to take these decisions. Now, of course, as always in these kind of problems, you use backward induction. So we start at the end and we say that actually this time tau 2, where you lift lockdown, has to be chosen optimally in the sense that tau 2 has to be chosen to minimize these costs. under the restriction that you can only lift the lockdown after you've actually introduced it. So now this now becomes an optimal stopping problem, because this time tau 2 is not necessarily a discrete time. Yeah, this can be a stopping time. So the way we model these decisions is to say that you have to choose a stopping time, and a stopping time, if you haven't come across these, is a random variable which has the property that at every point in time you can determine, whether the time has occurred or not. So it could be that you say, okay, I'm going to lift lockdown as soon as the number of infected patients has gone below a certain level. Or you could say, I exit lockdown once the number of recovered members of the population has risen above a certain threshold. Yeah, so those are all examples of stopping times, because at a particular point in time, you do not know when that time is going to be reached. So that gives the sort of the nested problem. And then, of course, we go one step further, because once we know when it is optimal to exit lockdown, we need to determine when it is optimal to enter lockdown. So we also need to determine an optimal stopping time, which tells us when to enter. So I suppose that the language here, maybe the jargon may be a bit odd, because we're talking about stopping something. It's just an accident of history, I suppose, that essentially, the way these things are typically modeled is that you're stopping observing something and you're acting. So you stop in action and you do something. So that's the stopping bit, if you like. So this gives us the mathematical problem to solve. Now, what we try to do in this paper is we're not simulating anything. We want to know whether solutions exist to this problem, and see if there's somehow a way of numerically ascertaining how these problems should be solved. It should also be noted, by the way, that as usual in dynamic programming, the solution to a problem like this consists of a tau 1, a tau 2, as well as the function v itself. Yeah, so this is a functional problem. Okay, so the way we solve this is by backward induction. So we start at the end, we look at this value here, see if we can find out what this value is. If so, we can then go one step back and find this value. And then once we establish that, we go one step further back and try and find this value here. Now, after you've exited lockdown, life all of a sudden becomes more simple, because you no longer have an option. So if your state of the world is X, here you should interpret X as being an I, number of infected, and a number of recovered. I got a bit lazy, I have to admit, in the notation. And you just compute the expected present value of your costs. And that can be computed explicitly once you're in an absorbing state. Yeah, once you're in an absorbing state, so a state from which you don't leave, then of course you have the current cost, and you know that you're going to incur that cost for the rest of eternity, because there's no moving out of that state anymore. So there's no randomness anymore. And you just get an integral from 0 to infinity of e to the power minus rho t times this constant number. So obviously then the present value of your cost is just the per period cost divided by rho. For any other state in the state space, we have a recurrent relation. We have a recurrence here. The function g here, this expectation, can be determined recursively. Now, because we have some absorbing states, that makes the numerics of our problem actually relatively straightforward, because in the absorbing states we can actually compute what the costs are, and then we can work our way backwards through this recursive relation to get this function g for every point in the state space. Okay, So that's one of the big advantages of using an SIR model, because you get these absorbing states. If you had a model of an endemic disease where someone who is infected is not recovered but becomes susceptible again, then it becomes more complicated. I'll say something more about that later. So that's the first bit solved. That's pretty straightforward. Yeah, there's also no decision to take anymore, so this is not an optimal stopping problem. So the next step becomes a little bit more complicated, because now we have to solve this problem here. So suppose that we are in lockdown. We then have to decide, choose a time tau, which gives us from time tau onwards the discounted value of this function that we've just computed, because we move from we leave the lockdown, so we're in the situation where we no longer have any options, and our expected costs are given by this function that we have just computed, plus the sum costs, of course, discounted to the current point in time, plus the running costs of being in lockdown from time 0 to time tau. Now that function we call function f. And the question, of course, is, well, is there a solution to this problem? And if there is a solution, what does it look like? And actually, well, this looks pretty awful, but it's actually not that problematic. If you ignore this bit here and the minimum operator here, you see a very similar recursive relation to the one I showed you on the previous slide. So when you're not taking action, there is simply a Bellman equation that governs, or a recursive relation that governs the value function. So at any point in time, you look at the cost, the current cost of the situation that you're in, and you correct it for the moves that might happen. So in a short period of time, nothing happens, and that happens with probability 1 minus this q, roughly speaking. You have to be a little bit careful how you interpret this. So over a short period of time, with that probability, you keep this cost C1, but of course it's still discounted over that short period of time. But with certain probabilities, things happen. With this probability lambda, another infected person arrives, and when that happens, with this probability, you move to another state, and therefore you need to evaluate the function in that state. And with a probability, another probability, there is an infected person who becomes recovered, and then you move to another state, and then you need to move, you need to look at the function value that you have at that point in the state space. Again, discounted, because this happens in a short period of time. So that gives this recursive relationship. But not only do we have this recursive relationship, we would have that if we had no decision to take whatsoever, we also have a decision to take. So at every point in time, you have to determine, well, what is best for me? Is it best to switch from lockdown back to herd immunity? Or do I stay in this mode and see what happens? Now, the value of seeing what happens is described by this recursive relation. The value of switching is given by this quantity here, because at the moment you switch, you get this function g, which is your expected costs from now till infinity of being back in the herd immunity mode, plus the sum costs. And at every point in time, you just take the minimum of the two. Okay, so that explains this Bellman equation here. And we can show that there exists a unique function that satisfies this relation, that function is equal to this infimum here, so is the function we're looking for, and that then the optimal time to exit is the first time that this function phi is no longer below the value of exercising the option. So essentially, the first time that this is the minimum of these two components. You know, that's when you make the switch. Okay, once we have that, we can go one step further back and look at the initial problem. Say, suppose that we're now at time 0, where we are not in lockdown, and we need to decide when to move into lockdown. That, of course, depends on that function that we have just found. And the question is then the same. Does an optimal stopping time exist, and can we find this function v? And it shouldn't come as too much of a surprise that the answer is yes, and is done in exactly the same way as I explained before. So you get a Bellman equation that says at any point in time you need to weigh the cost of immediate imposition of lockdown with the cost or the value of waiting a little bit longer. And as soon as the value of immediate action is, the cost of immediate action is lower than the cost of waiting, you should enter lockdown. I think it's important to emphasize here that these are all analytical results. So when we numerically implement these schemes, which we can because of the recursive structure, there are no issues around bias or anything that you might get in a simulation study. So just to put some meat on the bones here, let's look at a numerical example and see what happens. So here we have a list of parameter values for our model. They are taken from various sources, mainly related to the COVID pandemic, actually. So these parameters of infection rates, for example, are taken from the literature. So we see here that the probability of an infection is 0.3. Without lockdown, it's 0.15 in lockdown. We assume that the size of the host population is 500. So that basically means that we measure the population in chunks of 0.2%, if you like. Of course, you can increase this. You could make it 5 million if you wanted to. It just all becomes numerically a lot more tricky when you make n a lot larger. Okay, so we stick at 500 because after, if you increase from 500, nothing really changes very much. Okay, costs per patient and per day cost of lockdown are all taken from the literature. So just to quickly show you what happens to the epidemic, so without any decisions being taken. So infected, the brown area is the number of susceptible members of the population. Infected is brown, blue is the number of susceptible members, and red is the number of recovered. So time is on the horizontal axis, expected numbers of these infected, susceptible, and recovered members of the population are on the vertical axis. And you see that when you compare mode 0 to mode 1, that this is flattening the curve. This is what it looks like. So this brown peak here gets squashed. I think squashing the sombrero is the technical term in government circles these days. And that's exactly what you see happening here. So reducing the infection rate from 0.3 to 0.15 has this effect. Of course, it does mean that the number of susceptible people in the population is also larger. So what happens to our problem? What is the solution? Well, here it is. So what you see here is the number of infected members of the population on the horizontal axis, on the vertical axis, number of recovered. The blue area is the area where if you find yourself at time 0 in one of these states, you should enter lockdown straight away. The orange area consists of the states where if you find yourself in one of these states, you should exit, and you are in lockdown, then you should exit lockdown straight away. And the gray area is let me come back to that later. So what you see here is that, well, let me talk about the orange area first. The orange area says that actually you need to be quite close to absorption. Your chain needs to be quite close to absorption before you should leave lockdown. And that, of course, yeah, if like Nick and myself, you work in real options very often, then this makes perfect sense. There is an opportunity, there's a value of waiting, because once you've made this irreversible decision to leave lockdown, there's no way back. So you want to be sure enough that your epidemic is on the way out. So that means that you wait. Now that intuition then would also lead you to think, well, that would mean that you shouldn't impose lockdown too early, because you need to wait until you're sure enough that your lockdown is going to have the desired effect. But actually, that's not what we see. You should go in very early, because this area around the origin is blue. It's not as soon as the first infective appears, it's a little bit later, but not that much. And the reason for that is actually that you want to make sure that when you enter lockdown and have the sunk costs of entering lockdown, you benefit from it for long enough. The period in which you are in lockdown has to be long enough to warrant the cost of entering it in the first place. And that means you have to go in early. If you find yourself in this gray area, if you find out about the epidemic and you're in this gray area, there is still a positive probability that you will move into blue. So that there is, in the gray area, imposing a lockdown is not optimal, but there might be a point in time where it becomes optimal. If you're in this white area, if that's where you find out about the epidemic, you're too late. There's no point. Yeah, there's zero probability that you'll ever get to a stage where it is optimal to enter lockdown. So this leads us to conclude that you should go in early, but not if you're too late. Now, let me just say very briefly something about two extensions that we have. One is where we introduce health system constraints, where essentially we say that the cost per patient goes up, jumps, doubles, if the number of infected people reaches a certain threshold. In our case, we take 150. So that means that at that point you need Nightingale hospitals, everything becomes a lot more expensive, so you want to make sure that that doesn't happen. Then you see that still qualitatively everything looks a bit the same, it's just that the blue area has become a lot larger. So even if you discover the epidemic at a later point in time, you still enter lockdown, because the risk of your health system being overwhelmed is not worth it. It makes it even more important that you go into lockdown. The final extension that I'll quickly look at is, well, what about a third mode? Why, lockdown or herd immunity? Is there a halfway house? Could you introduce social distancing measures, for example? If you do that, then what we find qualitatively is that actually, it doesn't change the lockdown decision. You should never go from herd immunity to, well, bit of social distancing and then maybe later in lockdown. If it's optimal to have halfway measures, it's optimal to have a lockdown. So go in early, go in hard. However, exiting, it is optimal. So if you're somewhere in this, suppose you're in lockdown, you're in this white area, as soon as you reach this area here, it becomes optimal to move to the halfway house. And then once you reach this area here, you get rid of all the measures. So tapering off can be optimal, but sort of tapering in or easing in never is in this structure. And it's quite robust to parameter specifications. So to conclude, start lockdown early, leave lockdown in place until you're almost sure that the epidemic is on its way out. If you discover the epidemic too late, don't bother. Capacity concerns lead to earlier lockdown and later exit, as you would expect. And introducing a halfway house means that you should still go in with a full lockdown, but you can gradually phase out. Now, obviously, we made a number of heroic assumptions. First of all, we didn't take, recovered or death in our model is the same. Recovery or death is the same. you could, of course, extend this relatively straightforwardly to an SIRD model, so susceptible, infected, recovered, dead. It becomes numerically more complicated because your state space now becomes three-dimensional, but the model itself and the thinking behind it remains the same. A next step, of course, would be to look at repeated access to lockdown options. So what if at any point in time, if you're in a lockdown, you can leave it. If you're out of lockdown, you can enter it. What does that do to valuations? That problem, of course, becomes more problematic because you then get a sort of fixed point problem to solve, which is more difficult to do than what we have here. What if the disease is endemic rather than epidemic? So that if you're cured or you're recovered, at some point in time, you may become susceptible again. That's something we haven't looked at. That will change the model quite a bit because there's no absorption. And maybe very important here is, what if the parameters that govern the epidemic are not known in advance? So we're assuming that these infection and recovery rates are known. But what if you don't? What if you need a little bit of time to learn what the parameters are? In that case, I suspect you may find that actually you should wait a little bit with the lockdown so that you can learn more about the epidemic before you do anything. But I'm not sure about that at all. These are just some avenues of further research. I've gone on for far too long, so I'll stop here, and thank you very much for your attention. The paper, by the way, can be found on SSRN if you want to know more details.
Right, Jacco, would you like me to come in here?
Sure, yep.
So I've got a list here of some questions that people have asked, and there is a very popular question here in the box. And George is wondering if we could make any comments on an article, and the article here says that Sweden's most famous epidemiologist has admitted that going for herd immunity was not the best, the most optimal, or not the optimal decision. If we could make any comments on that.
Yes, so what Sweden seems to have been trying to do is to have this halfway house in the hope, this sort of intermediate mode, in the hope that they would never have to go into full lockdown. And as our results show, that's not an optimal thing. That's not an optimal thing to do. Now, in Sweden's defense, I would say that, of course, when this all started, the data, the parameter values for this epidemic weren't known. I mean, of course, there were similar kinds of diseases that we had some information about. So I'm not surprised by the fact that that he's saying that it wasn't optimal, because it what we found does concur with that. Although, of course, I have to give a health warning here. This is back of a cigarette packet kind of calculations in terms of we are really abstracting a lot from what is happening in the real world. But I still think the mechanisms that we describe here are quite broadly applicable. But yeah, so it wouldn't surprise me that he said that.
He was also wondering if we could make any comments on the fact that we choose our cost function to be linear. It says, well, actually, it would actually, so the lockdown cost that is linear in the number of infectives, actually, you could say that it's more convex, because the more severe lockdown is, the worse the long-term effects are in terms of unemployment and economic damage, and therefore it's a bit optimistic. He says that we choose it to be linear, and I've commented that it is interesting indeed, because there's different effects coming in. Because on the one hand, you could say, well, we should start lockdown earlier to have a higher probability of the virus dying out very quickly, but at the same time, you also might want to wait. So I was wondering if you had anything to add to that.
Yeah, so I mean, okay, so mathematically you can deal with it. Well, okay, you shouldn't go too much overboard, of course. But the arguments that we use in the proofs are quite robust against this formulation of, yeah. So we at no point do we use linearity of the of the cost function. So that's not crucial. So you could have convex costs. And I agree that if you had convex health costs, then I think that if you had convex costs, leaving lockdown would still take place late, obviously, because you don't want this virus to come back and then completely overwhelm. The lockdown costs, if you make those convex, well, okay, it depends a little bit on what you mean by convex. Convex in the state is not too difficult to deal with. However, if you were to make the cost function convex in time, so that the length of lockdown becomes an argument, then of course the length of time becomes part of your state space. So then you're in a three-dimensional state space, and we would have to redo everything we have done here. I mean, the nature of the problem doesn't change, so I suspect you'll still be able to prove that there is an optimal policy, but you might very well start seeing then that your policy is no longer just simply saying that you lift lockdown once you're infected and recovery numbers are okay. Time will then also become important. That then, of course, will also influence when you should enter lockdown. And I could very well imagine that then the prescription becomes that you should enter lockdown a little bit later because you don't want to be in lockdown for too long.
And I think another interesting element, so one of our main messages is as well that if you detect the virus too late, so which is what we see for some countries in the early stage of the epidemic, and it took quite a while before people started testing and before governments really took action. And we find that if you really wait too long with this, you might end up in a situation where the virus is so widespread that it's no longer optimal to take any action. And so if these costs are convex, any of these costs, this would also have implications for this message. So that will be really interesting. Okay, so another question that is popular is the question: why are we solving this mathematically, and why are we not using, for instance, simulations?
Well, okay, so
this is a question by Gregory. Sorry.
That's because okay, so this is partly personal taste, but I have no problem with simulations at all. But I like to have some analytical insight first into a problem. I think the advantage of using this kind of method is that it forces you to really strip back the problem to its core essence. And it really allows you to see what is happening, and then you can think about why it is happening. If you were to ask me to produce government advice on the basis of this, then of course I would start building from these humble beginnings a much more complicated model where I would happily simulate. It is true though that when you simulate these kind of optimal stopping problems, because typically what you find is that your value functions are convex, there is a built-in bias if you use, say, Monte Carlo methods to do these things. Of course, there are ways to get around it. I'm no expert on those techniques, but that's my understanding. But I just find it personally very difficult to understand the intuition if you have a very big model and you're doing a lot of simulations. What exactly is driving what? I think here we have. The analytics allows us to weave a narrative, if you like, that can help more quantitative researchers when they build simulation models. So I would see this as a first step rather than as the end station.
And I'm just keeping an eye on time, but Andreas was wondering, what is the advantage of this is coming back to the discussion on discrete time versus continuous time. What is the reason, what is the main advantage of using continuous time instead of discrete time?
It wouldn't, it is actually it makes it easier to bring in, I think, to bring in the randomness. You could do it in discrete time. I think that's not.
Maybe to add to that, this is related to a discussion that was in the Q&A about the fact that decisions are typically taken in discrete time. So you look at days and they're taken day by day. So since decisions are taken day by day, we could consider a discrete time model at the same time.
Yes, well, so it's okay. So here, I suppose that it's more. I think it's more thinking about it. Are we talking about epidemic time or decision time? So epidemic time, you might define as points in time where a change happens. So in our model, that is when the state jumps from one to the next. And the whole point is that we don't know when this, what that next change is going to be and how long it's going to take. So that is what's driving a lot of the results that we have in terms of the discounting, because you're discounting over uncertain periods of time. If you looked at sort of a decision time where you say, okay, every day we look at the data and we make a decision, I think you would still get fairly similar results. I don't think that would make an awful lot of a difference. It's just that there the graphs would become slightly, slightly different. I don't think it would make too much of a difference. It's we work in continuous time. It's that's what we do.
It's in a lot of setups, it's a lot easier to solve the problems as well. Yeah.
Yes, I think in terms of, if you were to take limits, then you have the whole apparatus of stochastic calculus at your disposal.
Yeah, which eases the robustness checks a little bit as well. Okay, so Steven was wondering if we could make any comments or could say how our conclusions would change if we were to consider repeated lockdowns. Or so in our model we assume that once you're recovered, once an agent is recovered, they stay recovered. But we've seen typically that after a while immunity fades, and so we might end up in a situation where you go back to an SRS model or SRDS, and how that would change our conclusions.
I think it would, I'll be very brief because I realize it's 2 o'clock. I think what you will see is that you go in even earlier because it's not as expensive to go in anymore. And indeed, you'll leave probably a little bit earlier as well, because you still have the option to go back into lockdown if you had to.
Cool. Great. Thank you so much, Jacco. Some new questions have popped up, which I haven't been able to read them all yet. I'm not sure how this really works because it's 2 o'clock now. What will be the best thing to do at this stage?
I think, it's probably best to close the session now because it's because of the time. But I think because we can have access to the Q&A, if there are particular questions that I think we can write a short answer to, we can send them out on Friday.
I'll also add our email addresses to the chat, that if people want to
that's fine.
Be in touch, then that's possible. Let me do it now.
Okay, but we'll also send these out on Friday with the links. So.
Yeah, I've been able to answer most questions, I think, in the Q&A. I don't think if it's recorded, people can see this, but yeah.
Okay, excellent. That's great. Thank you very much. It's 1:02, so I think we should stop. Thank you all very much.
Thank you, Jacco.